JEP 452, Key Encapsulation Mechanism API. Summary. Introduce an API for Key Encapsulation Mechanisms, KEMs, an encryption technique for securing symmetric keys using public key cryptography. Goals. 1. Enable applications to use KEM algorithms such as the RSA Key Encapsulation Mechanism, RSA KEM, the Elliptic Curve Integrated Encryption Scheme, ECHES, and candidate KEM algorithms for the National Institute of Standards and Technology, NIST, post-quantum cryptography standardization process. 2. Enable the use of KEMs in higher-level protocols such as transport-level security, TLS, and in cryptographic schemes such as hybrid public key encryption, HPKE, RFC 9180. 3. Allow security providers to implement KEM algorithms in either Java code or native code. 4. Include an implementation of the Diffie-Hellman KEM, KEM, defined in Section 4.1 of RFC 9180. Non-goals. 1. It is not a goal to include key pair generation in the KEM API. The existing key pair generator API is sufficient. 2. It is not a goal to support the ISO 18033-2 defined encryption option for the encapsulate function. 3. It is not a goal to support authenticated encapsulation and decapsulation functions as defined by RFC 9180. Motivation. Key encapsulation is a modern cryptographic technique that secures symmetric keys using asymmetric or public key cryptography. The traditional technique for doing so is to encrypt a randomly generated symmetric key with a public key, but that requires padding and can be difficult to prove secure. A key encapsulation mechanism, KEM, instead uses properties of the public key to derive a related symmetric key, which requires no padding. The concept of a KEM was introduced by Kramer and Shoup in Section 7.1 of Design and Analysis of Practical Public Key Encryption Schemes Secure Against Adaptive Chosen Ciphertext Attack. Shoup later proposed it as an ISO standard in Section 3.1 of a proposal for an ISO standard for public key encryption. It was accepted as ISO 18033-2 and published in May 2006. KEMs are a building block of hybrid public key encryption, HPKE. The NIST post-quantum cryptography, PQC, standardization process explicitly calls for KEMs and digital signature algorithms to be evaluated as candidates for the next generation of standard public key cryptography algorithms. The Diffie-Hellman key exchange step in TLS 1.3 can also be modeled as a KEM. KEMs will be an important tool for defending against quantum attacks. None of the existing cryptographic APIs in the Java platform is capable of representing KEMs in a natural way, see below. Implementers of third-party security providers have already expressed a need for a standard KEM API. It is time to add one to the Java platform. Description. A KEM consists of 3 functions. 1. A key pair generation function that returns a key pair containing a public key and a private key. 2. A key encapsulation function, called by the sender, that takes the receiver's public key and an encryption option. It returns a secret key K and a key encapsulation message, called ciphertext in ISO 18033-2. The sender sends the key encapsulation message to the receiver. 3. A key decapsulation function, called by the receiver, that takes the receiver's private key and the received key encapsulation message. It returns the secret key K. The key pair generation function is covered by the existing key pair generator API. We define a new class, KEM, for the encapsulation and decapsulation functions. Package javax.crypto. Public class decapsulate exception extends general security exception. Public final class KEM. Public static KEM get instance string alk, throws no such algorithm exception. Public static KEM get instance string alk, provider P, throws no such algorithm exception. Public static KEM get instance string alk, string P, throws no such algorithm exception. No such provider exception. Public static final class encapsulated, public encapsulated secret key byte, encapsulation, byte, params, public secret key, public byte, encapsulation, public byte, params. Public static final class encapsulator, string provider name, int secret size, / size of the shared secret. Int encapsulation size, / size of the key encapsulation message. Encapsulated encapsulate int from, into, string algorithm. Public encapsulator new encapsulator public key park, throws invalid key exception. Public encapsulator new encapsulator public key park, secure random SR, throws invalid key exception. Public encapsulator new encapsulator public key park, algorithm parameter spec, secure random SR, throws invalid algorithm parameter exception, invalid key exception. Public static final class decapsulator, string provider name, int secret size, / size of the shared secret. Int encapsulation size, / size of the key encapsulation message. Secret key decapsulate byte, encapsulation, throws decapsulate exception. Secret key decapsulate byte, encapsulation, int from, into, string algorithm, throws decapsulate exception. Public decapsulator new decapsulator private key SK, throws invalid key exception. Public decapsulator new decapsulator private key SK, algorithm parameter spec, throws invalid algorithm parameter exception, invalid key exception. The getInstance methods create a new chem object that implements the specified algorithm. The sender calls one of the new encapsulator methods. These methods take the receiver's public key and return an encapsulator object. The sender can then call one of that object's two encapsulate methods to get an encapsulated object, which contains a secret key and a key encapsulation message. The encapsulate method returns a key containing the full shared secret, with an algorithm name of generic. This key is usually passed to a key derivation function. The encapsulate from, to, algorithm method returns a key whose key material is a subarray of the shared secret with the given algorithm name. The receiver calls one of the new decapsulator methods. These methods take the receiver's private key and return a decapsulator object. The receiver can then call one of that object's two decapsulate methods, which take the received key encapsulation message and return the shared secret. The decapsulate encapsulation method returns the full shared secret with a generic algorithm, while the decapsulate encapsulation, from, to, algorithm, method returns a key with the user-specified key material and algorithm. A chem algorithm can define an algorithm parameter spec subclass to provide additional information to the full new encapsulator method. This is especially useful if the same key can be used to derive shared secrets in different ways. Instances of an algorithm parameter spec subclass should be immutable. If any of the information inside an algorithm parameter spec object needs to be transmitted along with the key encapsulation message so that the receiver is able to create a matching decapsulator, then it will be included as a byte array in the params field inside the encapsulated result. In that case, the security provider should provide an algorithm parameters implementation using the same algorithm name as the chem. The receiver can initiate such an algorithm parameters instance with the received params byte array and recover an algorithm parameter spec object to be used when it calls the new decapsulator method. Multiple concurrent invocations of the encapsulate or decapsulate methods of a particular encapsulator or decapsulator object, respectively, should be safe. Each invocation of an encapsulate method should generate a new shared secret and encapsulation. Here is an example using a hypothetical ABC chem. Before the key encapsulation and decapsulation, the receiver generates an ABC key pair and publishes the public key. / receiver side. Key pair generator G equals key pair generator dot get instance ABC, key pair KP equals G dot generate key pair, publish key KP dot get, public, / sender side. Chems equals chem dot get instance ABC chem, public key PKR equals retrieve key, a chem parameter specs equals new a chem parameter spec, chem encapsulator E equals chems dot new encapsulator PKR, specs, null, chem encapsulated enc equals E dot encapsulate, Secret key sex equals enc.key, send bytes enc.encapsulation, send bytes enc.params. / receiver side. Byte, m equals receive bytes, byte, params equals receive bytes, chem equals chem.get instance abc chem, algorithm parameters arc params equals algorithm parameters dot get instance abc chem, arc params dot init params, a chem parameter spec equals arc params dot get parameter spec a chem parameter spec dot class, chem decapsulator d equals chem dot new decapsulator kp dot get private, specra, secret key equals d dot decapsulate m. / sex and secret will be identical. Chem configurations. A single chem algorithm can have multiple configurations. Each configuration can accept different types of public or private keys, use different methods to derive the shared secrets, and emit different key encapsulation messages. Each configuration should map to a specific algorithm that creates a fixed-size shared secret and a fixed-size key encapsulation message. The configuration should be unambiguously determined by 3 pieces of information. 1. The algorithm name passed to a getInstance method. 2. The type of the key passed to a new encapsulator or new decapsulator method, and 3. The optional algorithm parameter spec object passed to a new encapsulator or new decapsulator method. For example, the Kyber family of chems could have a single algorithm named Kyber, but the implementation could support different configurations based on key types, for example, Kyber 512, Kyber 768, and Kyber 1024. Another example is the RSA chem family of chems. The algorithm name could simply be RSA chem, but the implementation could support different configurations based on different RSA key sizes and different key derivation function, KDF, settings. The different KDF settings could be conveyed via an as a chem parameter spec object. In both cases, the configuration can only be determined after one of the new encapsulator or new decapsulator methods is called. Delayed provider selection. The provider chosen for a given chem algorithm can depend not only upon the name of the algorithm passed to a getInstance method but also upon the key passed to a new encapsulator or new decapsulator method. The selection of the provider is thus delayed until one of those methods is called, just as in other cryptographic APIs such as cipher and key agreement. Each call of a new encapsulator or new decapsulator method can select a different provider. You can discover which provider is selected via the provider name methods of the encapsulator and decapsulator classes. The encapsulation size methods. Some higher-level protocols concatenate key encapsulation messages with other data directly, without providing any length information. For example, hybrid TLS key exchange concatenates 2 key encapsulation messages into a single key _exchange field, and RSA chem concatenates the key encapsulation message with the wrapped keying data. These protocols assume that the length of the key encapsulation message is fixed and well known once the chem configuration is fixed. We provide the encapsulation size methods to retrieve the size of the key encapsulation message in case an application needs to extract the key encapsulation message from such concatenated data. Shared secrets might not be extractable. All existing chem implementations return shared secrets in a byte array. However, a Java security provider might be backed by a native code implementation and the shared secret might not be extractable. Therefore, it is not always possible to return the shared secret in a byte array. For that reason, the encapsulate and decapsulate methods always return the shared secret in a secret key object. If the key is extractable, the format of the key must be raw and its getEncoded method must return either the full shared secret or the slice of the shared secret specified by the from and to parameters of an extended encapsulate or decapsulate method. If the key is not extractable, the key's getFormat and getEncoded methods must return null even though internally the key material is either the full shared secret or a slice of the shared secret. The Chem Service Provider Interface, SPI. A chem implementation must implement the ChemSPI interface. Package javax.crypto. Public interface ChemSPI. Interface encapsulator SPI, int engine secret size, int engine encapsulation size, chem encapsulated engine encapsulate int from, int to, string algorithm. Interface decapsulator SPI, int engine secret size, int engine encapsulation size, secret key engine decapsulate byte, encapsulation, int from, int to, string algorithm, throws decapsulate. Exception. Encapsulator SPI engine new encapsulator public key park, algorithm parameter spec, secure random SR, throws invalid algorithm parameter exception, invalid key exception, decapsulator SPI engine new decapsulator private key SK, algorithm parameter spec, throws invalid algorithm parameter exception, invalid key exception. An implementation must implement the encapsulator SPI and decapsulator SPI interfaces, and return objects of these types from the engine new encapsulator and engine new decapsulator methods of its ChemSPI implementation. Calls to the secret size, encapsulation size, encapsulate, and decapsulate methods of encapsulator and decapsulator objects are delegated to the engine secret size, engine encapsulation size, engine encapsulate, and engine decapsulate methods in the encapsulator SPI and decapsulator SPI implementations. An implementation of the engine encapsulate and engine decapsulate methods must be able to encapsulate or decapsulate keys with a generic algorithm, A from value of 0, and A to value of the shared secret's length. Otherwise, it can throw an unsupported operation exception if the combination of arguments is not supported because, for example, the algorithm name cannot be mapped to an internal key type, the size of the key does not match the algorithm, or the implementation does not support slicing the shared secret freely. Future work. Encryption options. ISO 18033-2 defines an encryption option for the encapsulate function because some asymmetric ciphers allow scheme-specific options to be passed to the encryption algorithm. However, this option is not mentioned in either RFC 9180 or NIST's PQC Chem API notes, so we do not include it here. If a compelling case for an algorithm that requires this option arises, then a future enhancement could introduce another overload of the encapsulate method that allows the inclusion of algorithm-specific parameters. Auth encap and auth decap functions. RFC 9180 defines two optional chem functions, auth encap and auth decap, which allow the sender to provide its own private key during the encapsulation process so that the receiver can be assured that the shared secret was generated by the holder of that private key. However, these two functions do not appear in any other chem definitions, so we do not include them here. Support for these functions could be added in a future enhancement. Alternatives. Use existing APIs. We considered using the existing key generator, key agreement, and cipher APIs to represent chems, but each of them has significant issues. Either they don't support the required feature set, or the API does not match the chem functions. 1. A key generator is able to generate a secret key, but not the key encapsulation message at the same time. As a workaround, we could potentially encode both the shared secret and the key encapsulation message as the encoded form of the secret key. However, this only works when the shared secret is extractable, and this is not always true, as discussed above. For keys that can be extracted, it still requires the application to extract the secret and the key encapsulation message from the encoded form of the secret key, which is complex and error-prone. Alternatively, we could store the key encapsulation message inside the secret key as a separate field. However, that would require a new secret key subclass that has a public method to retrieve the key encapsulation message. 2. A key agreement can return a key encapsulation message as a phase key and the shared secret, via different methods. However, a key agreement object is meant to be initialized with the caller's own private key, but for a chem there is no need to create a private key on the sender side. Also, the key encapsulation message of a chem is defined as an opaque byte array, but key agreement returns the phase key as a key object. New key factory and encoded key spec subclasses would be required to translate between key encapsulation messages and keys. 3. A cipher is able to wrap an existing key and then unwrap it. However, in a KEM the shared secret is generated by the encapsulation process. We could pass in a dummy or null key and store the actual shared secret in the output, but this has the same problem as key generator. It only works when the shared secret is extractable, and the application must extract the key and the key encapsulation message from the wrapped result. Moreover, wrapping a key and then unwrapping it should return the same key, but passing a dummy input to the wrap method does not conform to this convention. In short, each of these alternatives would be a hack to work around an API that was not designed to represent a KEM. Extra classes and methods would be required, and the implementations would be complex and fragile. Without a standard KEM API, security providers are likely to implement KEMs in inconsistent and awkward ways which will be difficult for developers to use. Include a key pair generation function. All KEM definitions contain a key pair generation function. We could have included such a function in the KEM API, but we chose not to do so since the existing key pair generator API was specifically designed for this purpose. Including an identical function in the KEM API could lead to confusion for provider implementers and for developers. Testing. We will add conformance tests on input, output, and exceptions, and the term known answer tests from RFC 9180.